ladies and gentlemen. Do we actually have any ladies here at all tonight? Today? We have one. Two. I'm sorry, two. This always makes me really, really sad to see. The state of our industry is really, really low on the gender diversity at the moment, and I think we deserve better. So thank you guys so much for being here, and if you are in a position to, please do help out with Rails Girls, Girls Who Code. Ask your employers whether they're looking into gender diversity. Thumbs up. We deserve more diverse insights into our industry and our craft, and the only way to do that is to get more different types of people involved. Okay, sorry. I'll get off my soapbox. And on to Lionel Richie. Do we all know who Lionel Richie is? Okay, I hear some ecstatic chuckles in the audience. The title of this talk is It Me You're Searching For? Full text search in Postgres. And I'm going to be talking a little bit about the full text search tools in the database that you're probably already using in your Rails app, which might just be good enough to use search in your app. A little bit about me. A little bit about me. My name is James, and I work for an open source decision-making software called Lumio, based out of New Zealand. And it's a software designed to help groups make decisions together in a non-hierarchical way. And like I say, we're open source, so if you're interested in contributing to open source, I coordinate the contributions. Please do get in contact with me. We're very happy to have beginners and experienced people alike. You can find me on the internet at gdpelican. On GitHub or Twitter. I don't tweet very much, so GitHub is recommended. You can look at every single commit I've made in the past 2 years. Or you can also feel free to shoot me an email at james@lumio.org. Okay, so what do we need to know about search? Out of curiosity, how many people are working on an app at the moment which has search functionality in it? Okay, cool, quite a lot of you. I think it's a really, really common use case, right? Because as soon as we get an app with a certain amount of data, we really want to have some way for users to filter and search by it. And so it's a really common use case, and it's a thing that I don't think we talk about very often. You know, when we go to Rails conferences and we converse on the internet, we talk at our jobs about these things, about Rails and Ruby in particular, or Ruby and Rails in particular. We talk a lot about CRUD. And we talk a lot about performance, and we talk a lot about APIs, and we talk a lot about Tender loves cats for some reason. And we talk a lot about lots of different things, but you don't hear the conversation about search too much. And since a vast majority of apps out there can really use a search function, it's really good as a Ruby programmer to know at least a little bit about it. So we're going to be exploring a few of the different options that you have in order to put search into your app. So let's see. Why do we need to know about search? This should read, what do we need to know about search? Sorry. The thing that I found when I kind of investigated search for a little while is that search is really hard. And search is really hard because search is subjective, and it's imprecise, and it's dependent on the user's context, right? If we have one user who's searching for a term, they may not be looking for the same document as a term that some other user is looking for. And so when I'm thinking about implementing a search solution, I'm really thinking about being good enough and iterating forward. Because I know that I'm not going to come up with a perfect solution. Definitely not right off the bat, probably not ever. Google's still working on it. And I'm not going to reproduce Google's search inside my app. So I really, really like to emphasize being good enough when we start off with search. And then we can add features later as we need to. Another thing about search is that it's also very dependent on your particular data. So most of the time when we're talking about performance of things, we're talking about the volume of our data. And that definitely affects the performance of our search. But another thing that affects the performance of our search is the actual data that we have, the type of data, how large it is, how many fields we're searching on. And this is going to be different for each individual use case. So more so than in a lot of different domains in our app, we have to be really, really conscious about doing user testing and knowing that our data is, in some ways, a unique snowflake that we have to treat specially. And so let's get out of the clouds for a little bit, and we'll talk about some of our options for full-text search. Who here is familiar with the story Goldilocks and the Three Bears? One person, really? Let me tell you a story. Goldilocks and the Three Bears is a children's fairy tale, which I believe is German. And it tells the story of this little girl who's traipsing through the woods with golden locks. And she comes across this empty house in the woods. And normally 3 bears live there. But at the time that she gets there, there's no bears there. And so she goes inside, and she sees a table on the inside. And she sees a table with 3 bowls of porridge on it. And she tries the first bowl of porridge, and it's too cold. And she tries the second bowl of porridge, and it's too hot. And then she tries the third porridge, and it's just right. So if we're looking at a search implementation, just like Goldilocks going into a stranger's house, stealing stuff, we have an option of several different types of porridge. So we'll look at what we want to implement, we'll look at our different options of porridge, and then we'll pick the best one for us. So let's start with the cold porridge. We'll start with the baby bear porridge. And the baby bear porridge is the I like operator in the search world. Many of you are probably familiar with the I like operator? Yes? Show of hands? Yes. Okay, cool. So the I like operator, if you're not familiar with it, is very similar to a regex match on a column. So here we have a singer's table, and we're going to select the name from it, and we want all the matches which match Lionel. We'll notice that we have 2 wildcard operators there, the percent signs, which means that anything in the string can come before or after Lionel, and the string will return. And so this has the benefit of being incredibly simple to implement, right? We have 1 line of code, we throw this into a where clause, and it just works, and it filters decently well. And it's really good for filtering small data sets. If we do quick and dirty searching, it tends to be on a single column with relatively small data sets. We still use it in Lumio at points. We'll use it to filter groups of usernames out of groups of members, which tend to be a single column on between 10 and 100 users, and it works really well for that. So it's good to be aware of, but it's not really appropriate for a full text search. And the reason it's not really appropriate is that it has no way to calculate relevance. Right, as soon as we start to get more than 3 or 4 matches back at a time, we want to know how good the match is, as opposed to our query. And iLike has no way to do this. It also doesn't do a great job of determining the intention of the search. There's lots of cases where it can go wrong or miss documents that we would otherwise want. For example, if we search for a phrase of 2 to 3 words, we're going to have to match the punctuation and the spelling exactly for a given document to return. Also, if we search for like the plural of a word and a document has the singular in it, it's not going to return this. So it's pretty weak. It's pretty weak porridge. So let's move on to our next porridge. And the next porridge is a much more powerful porridge. This is a third-party JSON search engine. And these tend to be open source third-party search solutions. They're powered by the Apache Lucene search engine, which is really quite good. And these are separate processes which run outside your app and have a copy of your search data, so that when your user performs a search, you can shoot off a request to this other process, and it will return search results for you. It's sort of a microservices approach to search. And these are very powerful solutions. They support faceting and aggregations and all kinds of languages and custom user queries, and there's really a lot of functionality there. And they're definitely fast enough for production use. Many, many people use these in production. 3 examples would be Elasticsearch, Sunspot, and Sphinx. Elasticsearch at the moment is the industry standard, but Sphinx is kind of an up-and-comer that's billing itself as kind of a lighter, easier to implement version. And so there's a couple of drawbacks that you should be aware of. This is definitely the most powerful solution for search. And if your app is primarily dependent on search, if you've got a site like Airbnb or Expedia or something like this where most of the time what your user wants to do is search, you probably want to go with this. But some of the drawbacks are that we are running on a separate process. We are duplicating our data across to a different database. And so this does 3 things. It complicates our architecture. I mean, we have to put in another stack of architecture. Elasticsearch is its own kind of technology that we may or may not have expertise in, whereas Postgres we're already using, and all we have to do is learn a couple of queries in order to make it work. This is a particular sticking point for Lumio because we're an open source project, and we really want to make sure that it's super, super easy to fork our code, download it, spin up an instance, dev on it, run your own instance, do all of these things. And adding another dependency to our tech stack is something that we want to try to avoid as much as possible. So if we can get away with Postgres, we definitely want to do that. And so, yes, if you're heavily relying on multiple facets or aggregations, if you need immaculate language support, go with the more powerful option. If you don't need the more powerful option, go with the less powerful option that simplifies your architecture. And so that brings us to our last porridge, the just right porridge, and that's Postgres full text search. And this comes installed with Postgres and has been around for a really long time. It came bundled with Postgres 8.3, which came out just around when Obama was coming into office. So if you're running a Rails app, you most likely have it in your stack already. It has the ability to rank and sort across columns and tables, and allows fine-grained control of rankings and search vectors, and it's definitely fast enough to use in production with a little bit of care, which I'll talk about. There's also a gem out there that you can use called PG Search. I'm not going to cover it in this talk, but I'm more than happy to answer, to share my experiences with it after the talk in questions, if you like. So let's talk about the mechanics of Postgres search for just a little bit. I like to think of it as being this three-part machine. And the three parts are, as you can see, the query, the vector, and the rank. And so these three parts are, the query is going to be the thing which interfaces with the text that the user inputs each time, whereas the vector is going to be the thing which interfaces with our documents, the underlying data that we're searching. And the rank is going to be the thing that compares the query and the vector and determines the relevance of those two things to one another. So we'll start with the query. And so in Postgres, there's two querying functions. There's toTS query, and then there's plain toTS query. And I'll talk about the difference between those in a second. But to start off, they both take strings, and they're going to convert them to this what we call a TS query. It's a TS query type of object. And it's basically an array of what we call lexemes. So we called this on the RubyDay here. And a couple of interesting things happened when we got back our query. The first thing is that we lost the. And the reason that we lost the is that the is a really, really common word in English, of course. And just because a document has the word the in it, it doesn't really mean that it's relevant to this query here. And so these are what we call stop words. And stop words are words that Postgres, they tend to be between the 200 and 250 most common words in a language, and we eliminate from the search entirely because they return so many results. And as we'll see a little bit later, it's a little bit expensive in order to calculate relevance. So if we think that something has no relevance at all, or if it has so little relevance as to not be significant, we really want to get rid of it. So we're getting rid of all of our stop words here. The other interesting thing is that we searched for RubyDay, and the thing that we got back here was RUBI. So it actually transformed the word. And the reason that it did that is that, so these are what we call lexemes. And if you're not familiar with the word lexemes is basically a word root. And the reason that we do this is because we want to be able to query for different words that are related to one another. So all of these words, eyes and eyeing and I and eyed, these all have the same root of I. And so we can imagine that if we're searching, we're doing a search and we search for eyes, we want to be able to get back words that are like eyeing and eyed. So it allows the search to be a little bit more intelligent about the documents that it's returning by reducing things down to their simpler language level. So let's go back to the difference between toTS query and plain toTS query. So if I put in a similar search query into toTS query, can everyone read this, by the way? Is this too small? Yes, thumbs up from the back, thanks, man. So if we select RubyDay from toTS query, it's actually going to error. It's not going to like that space in between Ruby and Day. And the reason that it's doing that is because it's expecting the query to be in a particular format, and the format is this thing called the standard Boolean format. And it just means that it accepts and, or, and not operators. So we can see if we try that query again and we pass it in Ruby and day as the query, then we get back the query that we're looking for. And so this actually requires a little bit, this is a more powerful solution, of course, because it allows us to use these different Boolean operators, but it also requires a little bit more processing on the Rails side to ensure that the query that we're putting into our database isn't going to blow up. And we can see down here an example of the not and or operators, the bang and the vertical pipe. If we use plain 2TS query, plain 2TS query is able to accept kind of raw user input, and it'll just string them together with the AND operator. So for example, if we query for RubyDay is happening down here, we're going to get a query that has the three lexemes Ruby, day, and happen. And I tend to prefer plain 2TS query just because it's simpler and tends to be good enough, but it's good to know that we have a little bit more advanced functionality if we need it. Okay, so moving on to the vector. We've got a query that's going to process the user input and transform it into this array of lexemes. So that's where we've gotten so far. The next step is to interface with the documents that we have in our search database. And so the way that we're going to do that is a similar function. We've got 2TS vector up here. It takes a string. In this case, it would be our search document. And it's going to convert it to what's essentially a hash. And the keys of the hash are going to be the same lexemes as we have in the TS query. And the values are going to be positional information. So we can see here we've got this nice vector here. And we've got day in position 2 and Ruby, the transformed Ruby, up here in position 1. And this is a really, really simple example. These tend to be much, much larger as documents can reach, many, very large sizes. And so if we look at a slightly meatier vector here, I've ganked some text off of the RubyDay website, and I've converted it to a TS vector. And we can see that we've got all sorts of cool search terms that this will match on. So if we search for any of these search terms, this is potentially a match. And in particular, if we search on Italian or on Ruby, we can see that these have multiple positions where they appear. We have Italian Ruby conference, and then we also have dedicated to the Ruby world. So Ruby appears twice. It's more likely to come back as a match. All right, so now we've got a query, and we've got a vector, and they're both essentially collections of lexemes. Now we're able to use a rank in order to compare these two things to determine how relevant they are. In Postgres, there's actually two steps to this. The first step is the double @ operator, and the second step is an actual ranking function. The reason that we have two steps is that the second step is actually quite time intensive. It takes a lot of processing power, relatively, in order to compare an array of lexemes and a huge hash of lexemes and determine how relevant they are. Whereas this double @ operator is actually really, really fast. But it doesn't give us a number. It doesn't tell us how relevant things are. It only tells us that they are relevant. So we do a first pass to determine which documents are relevant at all. And then of the documents that are relevant at all, those are the ones that we apply our ranking function to. And the way that we use this is the double @ operator goes between our query and our vector. That might be a little bit too small. But up here we can see that we're querying for Java week. And then our document here is Ruby Hack Day is 2 days away. And we get back an F, because those two things are not very relevant at all. None of the lexemes match. On the other hand, if we query for Ruby Day, that's probably relevant to our document here. And so we get a T, a true. And what we can do is we can throw this into the where clause of our SQL query, which will eliminate all of the documents which are not relevant at all. That way, when we call TS rank on our actual column, it's only going to process things which are somewhat relevant. And then we can rank them like this. It's a match. Is Tinder a thing in Turin? No? Okay, guess I won't download it. So the third part is TS rank. And I'm not going to go too much into the underlying mechanics of the ranking queries because they're a little bit archaic and they're a little bit underdocumented. But suffice it to say that they take a vector and they take a query and they'll output a number based on how relevant they are. And there's, again, two different ranking functions that we can use, which I'll talk about. So we can see here, if I've got a vector which says I can see it in your eyes, I can see it in your smile, and we call TS rank on that vector with eyes, we get a decent rank of 0.0607. Whereas if we search for eyes and smile, well, this is actually a better match. And so we get 0.0761. If we search for eyes and teeth, we only want documents which have eyes and teeth in them. We get a big fat 0, naturally. So this is TS rank. The other function that we can use is called TS rank CD. It also takes a vector and a query. In this case, CD stands for cover density. And cover density means that it takes into account the positional information that we've stored in our vector. So if we call TS rank CD, it's only going to look at how often the word appears, whereas cover density will apply additional weights if the words appear closer together. So if we search for RubyDay, and we have a document which has Ruby way at the beginning and way at the end, TS rank is going to rank that the same as if we have a document which has RubyDay together in a phrase. Whereas TS rank CD will say, oh, these words are really, really close together. This is probably quite a good match, and give it an additional weight. I generally recommend using TS rank CD. But again, it depends on the search data and the type of data that you have and the type of searches that your users are doing. So it will require some manual testing to figure out which one is best for your app. And there's also a really great article that's a little bit, it's a little bit dense, but it's really interesting. This is linked from the Postgres docs, and it talks about the ideas behind coming up with the cover density search, and has some really interesting information about how people search and how many terms people search for. So I recommend that. I'll publish these slides after this talk. Okay, so now we've got a basic bag of tricks for doing search. We can take a user input, we can compare it with our search document, and we can rank it based on relevance. So this is like MVP, the least amount of stuff that we can do in order to have a decent full text search. But there's some other cool stuff that Postgres has bundled in with it that we might want to be aware of. The first thing, and probably the most important thing, is custom weight fields. And this comes into account when we want to search across multiple columns, and especially when we want to weight columns differently. So if we have a model that has like a title and a description, if we search for the title, that's probably a better match than if a word appears in the title, it's probably going to be a better match when searched for than if it appears in the description. And so this has the ability to combine different vectors and apply weights to them. And we do that using this set weight function, which takes a TS vector and a weight. The weight is a single string, which can be A, B, C, or D. There's ways to get more weights, but for the most part, 4 weights is okay. And we can see that if we get a vector like this, it's actually applied the weight A to our hash here, so that those terms will be weighted very heavily when we search on them. And this isn't very useful by itself, of course. It really is only useful when we combine this with other vectors, which have more or less weight. So if we take our example of having a Ruby conference in Turin, Italy, and then RubyDay, this would be the title and the description up here. RubyDay would be weighted really, really heavily. Ruby conference in Turin, Italy would be weighted less heavily as a C. Another example, we can take, like if we have a song object, and that song has a title, chorus, singer, lyrics. We'll come into this example a little bit later. But we can set different weights to each column. So if we find a match in the title, it's going to be weighted very heavily. If we find a match in the chorus or the singer, it'll be weighted less heavily. And the lyrics will be weighted even less heavily than that. These weights are relative weights. And the defaults are 1.0, 0.5, 0.3, and 0.1. And that means that if we find a match in an A column, it's going to take 10 matches in a D column in order for that to be as relevant. And there are ways to change the default weights as well. Okay, I want to move on from that a little bit because we'll look at it more later. Another thing we might want to do is search in another language. Postgres has pretty decent language support out of the box. So let's take our example here. We're going to take a 2TS query of Ochio. And then is anybody willing to volunteer a proper pronunciation of this phrase up here? Oh, prego. Beautiful. This translates to, I can see it in your eyes. And so if we search for Ochio, we should really get a match on this document, right? We're talking about eyes, and we're searching for I. This should really be a match, but it's not. We can see there's an F here. And let's see, why is that? Well, if we call just 2TS query on Ochio, we get Ochio back. But both the TS query and TS vector will accept this optional language parameter in the first argument. And this will allow us to use a different dictionary. So remember how I said that it'll take words in the document and translate. It'll take words in the document and it'll translate them to lexemes. The way that it does that is it looks them up in a dictionary. And the English dictionary is the one by default. So here it's trying to look in an English dictionary for the word Ochio, and it's finding nothing, because of course Ochio is not an English word. But there are plenty of other dictionaries that come bundled with Postgres by default, and you can actually define your own and tweak the existing ones if you need to. And so you can specify which dictionary you want to use by passing it in to the first argument of both the query and the vector. Doing a query of the infamous pg catalog pgds dict table will give us a list of the default of the packages that come bundled with Postgres. You can see that we've got Italian here. We've also got Romanian, Russian, Spanish, English, Dutch. So it's actually quite powerful for something that comes bundled with your existing database software. And so here, if we pass in Italian to both, then we get back true. Beautiful. Oh, and David Hasselhoff approves. Yeah, okay. I forgot I put that in there. All right, so another little trick in our bag of tricks that might be useful is getting a result headline, right? We're matching things with these massive documents, and one thing that might be useful is if we're showing a search result, we don't want to show them this massive block of text that's like, oh, we found it in this. We'd rather show just a little snippet of where we found it. And of course, we can do this with regex matching in Rails if we want to, but Postgres has this really nice TS headline function built into it. And this will take a string, our document, and the TS query. It can't take the vector because, remember, we've stripped out the stop words and the punctuation and the capitalization. So it doesn't quite have enough information from the vector in order to generate a snippet. So it'll take the actual document, and it'll compare the query with the document, and it'll spit us out a nice little blurb of where in the document it's found the result. And we can see that it's actually got a little bit of HTML highlighting up here. So eyes will come out in bold by default if we render this in our view. There's a couple of nifty options with this. We can change the way we want to render this if we like with this start cell and stop cell. So we can change this to italic if we like. Or we could put a div or a span or something on it with a class so we can spot style it however we like. And it also takes a min words and max words argument. So we can specify that the snippet that comes back is between 5 and 7 words. And this function is actually really well documented, so you can check out the docs if you want to learn more. So let's look at our current bag of tricks. We can convert user input to lexemes. We can convert stored database documents to ordered lexemes. We can determine which documents match our input. We can rank results based on the quality of matches. We can combine multiple vectors and we can weight them. We can search in multiple languages, and we can get a snippet of where in the document we've matched. This is actually quite a bit of functionality. And I think it's probably enough for us to actually implement something. So I've been talking a lot and not showing a lot of code, but I want to show just a little bit of code. So we're going to make a simplistic search engine. We're going to make a little database of song lyrics, and we're going to make it searchable. So I've got these 5 wonderful love ballads here, and I'm going to put them in a database. And I've actually open sourced this, so you can follow along at home if you like, and it's live on rubyday.herokuapp.com. So first we're going to have a really simple database schema. We've got a singer, and we've got a song model. And a singer has many songs, and it belongs to a singer. And we'll have some seed records. So we're going to stick our seed records. We've got 4 singers and 5 songs that we can search. We've got a whole bunch of lyrics associated with them. And we've got a view. And the view is going to basically display a table, and it's going to show the title, the duration, the name of the song, and the rank and headline for our matches. And we've got a really simple controller where we take a query, and we take some songs, and we render out our aforementioned view. We're going to call this full text method on song as a scope. And I've written 2 iterations of this. And we'll take a look at the first iteration and see what we like or don't like about it, and then we'll go on to a second one. So here we've got 3 select statements, a join statement, a where statement, and order. We're composing a SQL query. This is all happening in one single SQL query, this search. This first line up here is saying select all the things that you would normally select when you do a find. And then we're also selecting a headline. So we can see that we're passing in the lyrics column to the headline, and we're also passing in our query. Notice that I've got some duplication about the plain 2TS query. I don't mind this so much because this is a blazing fast method. It doesn't take too long to parse user input, especially because it's usually only 2 or 3 terms long at most. And then the interesting part of this is we've got our 2 ranking functions. So we've got the TS rank CD, and then we've also got our double @ operator down here. And those are both taking a search vector. And when we call search vector, we're combining 3 vectors. One on our songs, one on our singers, one on our song title, one on our singers, and one on our song lyrics here. This is why we're joining on singer up here. And we're saying that the song title is really important, so we're going to rank that as A. The singer's name is not as important, so we'll rank it as B, and the lyrics aren't as important at all, so we'll rank it as D. And then when it comes back, we'll order them by rank descending. So who can tell me what kind of sucks about this implementation? Does anyone see what sucks? The songs. These are my favorite, but thank you for saying that. Yes, and what else? Okay. So the thing that I think that sucks about this implementation is that we're calling the search vector twice. And this is actually a really intensive operation, right? So every time we call 2TS vector songs.lyrics, we have to parse the entirety of Total Eclipse of the Sun by Bonnie Tyler, not just once, but twice, every time we do a search query. This is a really expensive thing, and we're doing it in both levels of our rank up here. And if we think about it, the only time that the vector is going to change is when we change the record, right? The only time that the lyrics are going to change is if we update the lyrics in the database. So this is actually an operation that doesn't have to happen every time we search. This is an operation that we can do when we save a record and then store it for later. So this is the beginning of search indices, right? Search data. Data that's really easily searchable, as opposed to the full on document. Thank you. So let's take a look at iteration 2. In iteration 2, we're going to throw in this before save. Don't recommend using before save in production, but this is a sample app. So every time we save a record, we're going to do this set search vector. So this is happening right before we put it into the database. And we can see that we've added a column to our songs down here. And Postgres actually has a type called TS vector. So similar to a string or a text or an integer type in Postgres, we can have a TS vector column, which will store vectors for us. And so right before we save a record, we're going to call this same SQL query up here, and we're going to save it to a search vector. So the search vector gets set, we save it, it's stored in the database, we don't have to worry about it until it changes again. And so now let's take a look at our scope. And our scope looks very, very similar. We can see that we've lost the join on singer up here, which is nice, because we've already stored the singer information in our vector, so we don't have to join on that anymore. And instead of calling a method called search vector in our 2 ranking functions, here and here, we're just calling the column on song. And so this is actually a quite nice implementation, simplistic implementation here. One of the big benefits of doing this in a scope is that we can chain additional queries to it and have them happen in the same SQL query. So, for example, if we have a singer, Lionel Richie, my favorite, we do singer.findByName, Lionel Richie, and then we can just do this really, really nice query here, which is full text of hello, and then add where singer is Lionel, and then it will only return matches for which the singer is Lionel. And we can do this with any sort of scope we like. So we can do it for only active records, or only records after a certain time. So it's a really nice way in order for us to add features in a way that doesn't muddy up our search implementation. That's it for our sample app. If I have a little time at the end, I'm happy to spin it up and take a look at it. If you're interested in this stuff and you want to take a look at some actual production implementations in the wild, do feel free to go check out Lumio's implementation. It's a slightly more complicated of the thing I just presented. It's got support for custom weights across tables and has many relationships. We can use filtering and pagination with scopes, like I just described. It's got a nice indexing strategy to take a look at, and it uses some subqueries to increase the SQL query speed. On our app, which may be quite different from your app, we're seeing search queries take about 57 milliseconds per query. And on the indexing side, when we index our search records, it takes an average of 27 milliseconds. So this is quite good for production. If you're into a really, really hairy search implementation, which is very, very advanced and nice, take a look at Discourse's search implementation. They've got lots of cool support for things like advanced user queries, faceting and aggregations. They can search in Chinese, and they actually default to the I like search when they need it. So there's lots of cool stuff in there for advanced features if you're looking to expand.